Here we are again on the 2018 Grand HPC Road Trip, and we are at NREL, and I just got the best tour in the world from...
Hi, I'm Steve Hammond. I'm Director of Computational Science at the National Renewable Energy Laboratory.
And if you want to know anything about liquid cooling, if you want to see liquid cooling in action, this is the place to go. And using that waste heat. And tell us a little bit about that.
Well, we focused on three things in the data center. First, on the energy efficiency, so the PUE. So our current PUE is 1.03, so that's like world-leading power usage effectiveness.
And by the way, he's rounding up. It's actually 1.027. So he's modest,
I stand
very
corrected.
modest.
It's the instantaneous 1.027. Part of the feature of the data center is waste heat capture and reuse, which you can do effectively with liquid cooling. And then lastly, in a collaboration with Sandia National Laboratories and Johnson Controls, we have a dry cooling system that enabled us to reduce our water usage in the data center by half. So we've saved 2.2 million gallons of water, enough to fill 4 Olympic swimming pools in the last 2 years.
Wow, that's incredible. And you were also saying that the heating that you're getting out of the system has allowed you to save roughly a megawatt a year in electricity.
So we, compared to a typical data center, our efficiency with the PUE of 1.03, I'll round up, that allows us to save about $800,000 a year in electricity expense.
Just on the basis of a low PUE.
Just on the basis of we don't have a lot of extraneous utility needs for losses and the cooling side. And then because we capture and reuse the waste heat, our data center is integrated into the larger research facility. So we capture and use the waste heat from our HPC system. So we save another approximately $200,000 that we would otherwise have to pay to heat the building.
Not
so
too
office
shabby.
Space and lab space. So in aggregate, that gives us about $1 million a year of OpEx savings. And for a data center that costs less to build, more efficient. So some of the significant costs in data centers, if you think about HPC data centers, is chillers. So they're expensive and they tend to be very energy demanding. So we have a chillerless design. We use evaporative cooling, and then more recently with the thermosiphon, it's a Blue Stream product now. We had it as a prototype from Johnson Controls. So there are a little over half the year when we can rely strictly on the thermosiphon unit, and we turn our evaporative cooling off. And we demonstrated that we can reduce our water usage in half without compromising on our extreme energy efficiency.
Wow. And we just took a look at your newest system, Eagle. Can you tell us a little bit about it?
So Eagle was installed in September. It's a Apollo 8600 prominently. There's 7 petaflops of Intel Xeon chips, dual socket nodes, another petaflop of NVIDIA Volta chips. So that's a 8 petaflop system in total. It's a hybrid sort of CPU node or CPU GPU node system, and it's replacing Peregrine. It's a little over 3x the capability of Peregrine in the same footprint. It uses just slight additional amount of power for that 3-fold increase in computational capability.
That's incredible. That is very, very interesting. Where do you think we're going with ultra efficient computing, liquid cooling, all of that? One of the things that I've been hearing from vendors is that the TDP is going up on chips, maybe even a double. How are we going to deal with that? We're going to have liquid cooling, aren't we?
Yes, so sort of a rule of thumb is somewhere around 30 kilowatts in a rack. Below that, you can air cool, you can, but you have a lot of fan energy. Above 30 kilowatts, it becomes increasingly difficult to get the heat out of the center of the rack or top of rack issues. So our racks are somewhere north of 40, anywhere from 40 to 60 racks, depending on which specific rack we're talking about.
40 to 60 kW per rack?
kW per rack.
Okay.
It would be extremely difficult, extremely inefficient to cool that effectively with air only.
Yeah. I mean, you'd have to have enough fan to blow it across the room.
Yes.
But
Yeah, and so our approach, I mean, in terms of liquid cooling, the way we think about it is from thermodynamics. So liquid as a heat exchange medium, a juice glass of water has a cooling capacity equivalent to a room full of air.
wow,
And the pump energy to move that juice glass of water around relative to the fan energy needed to move roomfuls of air around is 10x more efficient to do the liquid cooling pump. So in aggregate, I mean, as a heat exchange medium, liquids are 1,000 times more effective than air.
yes,
Right? Anybody who owns a down jacket knows air is a really good insulator. You can wear your down jacket or sleeping bag. You've got, dual pane windows in your house for efficiency. Air is not a good conductor of thermals. So we work with thermodynamics, and that has been a tremendous benefit to us.
but is there enough headroom in typical liquid cooling today to continue cooling even if the BTUs coming off of a processor double?
Yes, I think so. To do the heat exchange, you just increase your flow rates a bit.
Okay.
So it's a matter of getting good heat exchange. Get the heat exchange close to where the heat is being produced,
Okay.
and then have enough flow across that interface to allow the heat from the chips to get into the cooling.
So a flow rate and maybe a flow quantity
Right.
adjustment, but plenty of headroom
Yeah,
to
right.
handle even a doubling. Okay.
Yeah. Yeah.
That's good to
one
know.
of the things, a bandwagon that I'm on.
Yeah.
I mentioned to you earlier. If the data center ferry gave me one wish, I would love to have a common set of interfaces, connection points at the back of the rack.
Yes.
We work with 6 different vendors in terms of cooling, and they each have different cooling or connector types, whether it's 2-inch or 1.5 or 1.75 inches.
All different. Quick disconnects, completely different.
But and a pet peeve of mine is the supply and return are the same, so it's easy for a
To
well-intentioned
loop
build
yourself up.
to make a connection mistake. So it would be ideal if they all agreed on the same standard of just what that interface is.
Yes.
They can innovate.
They can
within the
innovate
rack.
beyond that.
Yeah.
Lots of innovation
Just
room.
Pick a connection type for the supply and something different for the return, and just agree. Then a facility owner or the data center manager doesn't have to say, "Oh, I'm installing 4 more racks from this vendor, and I've got to run a different connector type for that." It would just it would make it
Be so
easier
much
for us.
better. And can you describe this data center ferry? Because I have not heard that term before.
Well, so far I'd say the data center ferry has smiled upon us.
Okay.
because When we started this effort in 2006, everybody thought I was a complete lunatic to go to liquid cooling.
Really?
Everybody knows
In 2006?
Yes, we started planning for this in 2006. You couldn't buy liquid cooled systems,
No.
but we followed the Wayne Gretzky analogy. We went to where we thought the puck was going as opposed
Yeah.
to where the puck was, and wanting to make sure that we were able to effectively cool the systems at what we saw was increasing power densities. So we committed to liquid cooling in 2006 before we could buy liquid cooled systems. We did have a backup plan, but we were fortunate that 3 different vendors in 2011 bid liquid cooled systems that were compliant. And it happened that Hewlett Packard at that time provided the best value for
Yeah.
our this.
You know who else committed to liquid cooling in 2006? Me. That's when I built my first liquid cooled system. And you're right. I mean, you could not get a liquid cooled system. You could get hobbyist stuff, gamer stuff. But
Yeah, this
you
has been
looking
really-
for data center quality gear, not then. Yeah, it was too soon.
This has been incredibly satisfying to have a vision, at NREL be supported to do something innovative and at the very leading edge. To have a partner with HP that we worked with, to say yes, we can do that, we can deliver it, working closely in partnership. So I've said this before, part of the role of the national labs in aggregate is to help work with industry to do the things that they would like to do and help do it at lower risk and maybe shorter time to market, in a way that we can help industry
pull them along.
Yeah. So they have a better product to market, and we get a product that we would really like to have to meet our R&D needs and to support the laboratory mission.
Fantastic. Okay,
All right.
introduce yourself.
So I'm Dr. Nicholas Bernhardt-Lupo. I work here in the Computational Science Center, part of the Analysis Division. Our job is to, like Dave said, that we want to bring in data from the supercomputer and work with our researchers to bring their data into this space so they can look at their data better and interact with their data in new ways, shorten the distance between seeing their data and understanding their data.
And I'm wearing the glasses, and I can tell that this is cued to my head movement at least a little bit.
Just enough to give you this stereo parallax, kind of like you have at the movie theater. We have that stereo screen. But unlike the stereo screen, we do have a special pair of glasses here that I'm just going to have you swap out with.
Okay.
This one's special in that it's tracked by the computer. So I just wanted to give you that stereo first, and then as you
Give me a quick view of that to the camera. It's got these little things.
put that on, I'll
Put that around my huge head.
Perfect.
There we go.
All right. Now you can walk right into this space. You can stick your head right inside that turbine tunnel there.
Wow.
I'm going to grab my controller so I can move us to places you can't walk to.
Okay. I feel like I should. I mean, this is good enough that it feels like I should be able to touch it.
Right, and we kind of want to start getting towards the place where we can actually enable that and actually reach.
That would be pretty cool.
I'm going to show you how close we can get to that. In just a
Okay.
second here.
You want me to hold the mic while you do that?
Sure, I just want to kind of show you that what we have here is we have a computational fluid dynamics simulation of a wind farm, right? We have these 4 turbines in the front, and they're generating this big blue mass, and the big blue mass is the low velocity wake created by these turbines as they extract energy from the incoming flow. So it's basically used air in this context.
Sure.
Now, the reason why we care is because there aren't just 4 turbines, there are actually 14 turbines in total in this simulation. So let's go on a little trip and let's go find those other turbines. Here we go.
Okay. Whoa. Wow.
Flying down this wake, here's a turbine here,
Okay.
and there's another turbine over here. So all
These
those
guys are getting some pretty choppy air back here.
yeah, it's really, really bad. I'm going to turn on another display here. Let me zip to the front here. And turn on Q criterion, which is a measure of turbulence.
Okay.
So there's blue is just the slow-moving air. Yellow is where the turbulence is really, really high. And you can see, as we go about 300 meters down the line, it just turns
Wow.
into this nasty mess, right?
Yeah.
And everything is being blown into the face of this turbine. Now, it's getting slow-moving air, so that means you're not getting as much energy generated by that turbine, which means you're not getting as much money as you want.
Sure.
That guy.
Sure.
And also, all this turbulence means that you're also spending a lot more maintenance costs.
Oh.
So this is a double hit whammy here. And you're not going to be as profitable as you want to be in a situation like this. And this does happen on a number of older wind farms.
So is this a positioning problem?
It's a positioning problem. And I mean, you can't see these structures in real life, right? So if you're building a new wind farm, how do you know where you're supposed to put your turbines, right? It's kind of hard to know.
Well, you got to have one of these.
Unless you do the simulations,
You
right?
better do
those,
this, yeah.
So those older wind farms that didn't have these simulations are poorly sited because they didn't
Idiots.
have they didn't have any way to figure it out. So what we have to do is we have to figure out some ways of mitigating this because these turbines are sunk into concrete.
Yeah, you're not going to move
So
them.
you can't move them anymore.
No.
So we ask questions like, hey, can you take these front turbines and yaw them like 50 degrees, 15 degrees? Can you steer them around a little bit? Can you steer that
Okay.
wake off the guys to the rear? Can you play that optimization
Yeah.
problem? So
Maybe the shape of the blades a little bit.
There's a whole
might be a little
ton-
something there.
a ton of different variables for that.
Maybe a shroud. Who
Exactly.
knows?
So this is just a way that we can look at this data. This is a 200 terabyte data set.
Wow.
So just looking at it, just reading it off disk can be difficult, right? So
Yeah.
we worked with the researchers to compress their data in a novel way so they can actually look at it in 3D.
That is nearly the size of my Outlook file.
It's huge.
It's big. It's very big.
So, I mean, before what the researchers typically did is they took a 2D hub height slice of this
Okay.
volume and they just look at it kind of like a CAT scan. And they just look at that and try to do their research with that.
Oh, that's not going to help enough.
Exactly. You can
That's-
imagine you're missing out on a lot of context on the side. You can see
Oh,
the nice
yeah.
sinusoidal wave action. You're missing out on all this information that you need to help figure out to characterize
And the
these
thing
waves.
is, I mean, if you're not visualizing this, you're reading it on a spreadsheet.
Yes.
And this is not going to jump out at you on a
Or you're looking at
spreadsheet.
statistics. And
Or
those
you're looking at
statistics-
stats.
Yeah, and those things can be quite misleading.
Yes.
They might show you something.
Well, it's a bunch of averages.
Yeah.
It's a whole. I mean, you've got to
Exactly.
reduce the number of data points. So you're averaging, but you're not seeing the outliers like you're seeing here or the patterns.
Absolutely. So this space is great to look at these large data sets, but let me just quickly swap to another data set
Okay.
to show you what interactivity we do have in this space.
Sure.
Let me just hand you this.
Okay.
And I'm going to be right back. Give me just 1 second.
It's like a magician setting up a trick.
So it's not the inside of a nuclear reactor, but it's pretty cool, right?
Yeah. All right.
Okay.
All right. So this data set is from our vehicle technologies office.
Oh,
And their job is to try and improve the heating and cooling inside electric vehicles. Because if
Okay.
you have an electric vehicle, I mean, if you turn on the heater, you don't have an engine to take the heat from.
no.
So you've got to make it. It's got to take the power from your batteries, which decreases your range. So if you're in, say, a Nissan Leaf and you turn on your heater, you could lose up to half your range.
Ho, 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 ho.
Some cars are like that. Some newer ones are getting better because of our research like this. And research that Ford does. This is a Ford Focus.
Okay.
And they're trying to improve the heating and cooling inside this vehicle. I think this scenario is a cooling scenario. We have this vent over the mannequin's head.
Okay.
And you see it's kind of
Sure.
it's kind of oddly positioned. So what we want to do is we want to figure out where this airflow is going from this vent. So I'm just going to take my controller, hold it inside the car, and push a button. Now we can
Oh, that is
interactively figure out
impressive.
what's going on and probe the space. So we have this nice blue air coming outside the vent, and we have red because the sun is heating up the dash
Sure.
and the glass there. So why don't you take the controller here,
Okay.
just press and hold that green button, and start painting inside the car with it. Perfect. So now you can interactively probe this vector field in a way that you cannot do on a laptop or desktop. And you can
I don't probe anybody's vector field unless I know them. I'm just saying.
It's be friends worth taking to dinner. And you can
This
see
is very impressive.
This is an easier way of looking at it. I mean, the data you can see it's very complex, very chaotic. So in 2D, you get a lot of overdraw. These things sort of plot themselves out, so you don't see a lot of what's going on until you can sort of like cull the question space.
That's highly
Here's a way of doing
impressive. That is.
So that's just
That's a
one way.
lot of data that's being manipulated in real time there.
Yeah, so this is what we try to bring to the data, is this sort of interactivity.
I want to make sure I'm catching all this, and I think I am.
Yeah.
Mostly the back seat, but no, I got him. Okay.
Drop a point here so you can get that. So yeah, this is just another way that we can look at the data.
That's
Help
really
researchers
impressive.
Get a quantitative, or in this case, qualitative view of the data. Here they found that there was a lot more airflow between the driver and the door and underneath the seats.
Really?
Realized was there until they brought it into the space, just because they just couldn't see it in their 2D plots and their 2D
And
charts.
what's going on with the big silver band sort of in the middle?
So silver is sort of a neutral temperature there. So
Okay.
that's just where it's sort of a nice normal temperature.
And it looks like it's really roaring through the underneath of that head
exactly
of the
so a lot of
headrest.
flow under there. That's something you just don't think about.
No, you
until
don't.
actually see
You
it.
don't.
Yeah.
And I might want to fix that if I'm somebody.
Yeah,
I might
exactly.
want to have that doing something else.
If you're doing zonal cooling strategies, you're going to want to try a better curtain to try and close
Yeah.
these things off. So that's just one of the ways we can look at the data.
It's very impressive.
So we go from here, like we do the whole mission space lab, so we
Uh-huh.
do a lot of CFD work, computational fluid dynamics work, just because it maps so well, 3D to 3D. We do things that are more abstract, like power flow visualization.
Okay.
We can do more things like virtual construction, so people can give us, their technical drawings of an object
Sure.
they want to build. We'll give them a prop. Like this is a pool noodle, but it's got a tracker on it.
Okay.
So that they can actually, build an object in this space. This will be like a strut to the computer. And They
Okay.
can put it all together to make sure.
And
it
see where
fits.
the airflow is around it.
Or just make sure their
Or
parts
whatever.
fit before they go to
Okay. Oh,
fabrication.
good. Okay.
Exactly. We can also do things like financial modeling, and investment modeling.
Sure.
In the space, and we can bring that data up in a very abstract way for our researchers to work with. And in that case, they can actually ask a question like, if I'm, incentivize biofuels in 50 years, do I get an uptake, and have that get sent off to the supercomputer to simulate that result, show them what's going on in a very interactive, 10-second delay sort of thing.
This is hugely incredible. Thank you so much for sharing it.
My pleasure. My pleasure.
I am pumped. This is cool. Well, thank you again, and I'm really glad we had this time and we did this stop.
I'm very happy to show this to you.
And we will talk to you again soon and see you at Supercomputing.
I don't think I'll be at supercomputer.
You're not going to be at
No, they
Supercomputing.
keep me chained to that desk over there.
Okay.
So-
You stay here.
Yeah, someone's got to hurry.
Penny's going there.
I think he might be. We'll have to see.
So you stay here, work on this stuff. I'll go to Supercomputing.